Hello, YouTubers. Let's take a look at this interesting problem. Best position for a service center. By the way, it's a Citadel interview problem. In order to solve this, we need some mathematical intuition. And this intuition is quite useful even beyond the problem itself. Let's take a look. Problem description is quite straightforward. Here we have a map. On this map, we have some customers in different locations. We want to build a service center so that the total distance to those customers will be minimized. This is a formula. This is our service center's location. And for each customer, we calculate the distance and we add all the distance together. We want the total sum to be minimized. The straightforward solution is we scan the whole map and for each location, we calculate this formula and the smallest total distance will be our answer. Let's take this approach. For each data center's location, we are going to calculate the total. We will write this formula. Now we have this formula written. We can check all the points in this map. Okay, now we have scanned through the whole map. The smallest one is our answer. As you can see, this is the right answer for this example. Total distance is 4. 1, 2, 3, 4. For this example, the total distance is the distance of this one plus this one. Okay, let's submit. Wait. Our goal is to scan the whole map and find the minimum total distance, but we didn't do that. We only checked several points on this map. We checked this point, this point, this point, this point, this point. We checked this point, this point, this point, this point, this point. But there are numerous points we didn't check. What happens to the points here? There are numerous points. In this area, this area, in this area, we didn't check them. We only checked a few points with x, y as an integer. So if the service center didn't fall on integer coordinates, the answer will be wrong. Let's create that situation. Give some randomness. So our answer will be wrong. As you can see, this is the wrong answer. Since on the map there are numerous points, infinite number of points, scan through all of them is impossible. So we need to rethink about our approach. Let's start with a one-dimensional case. We only have 2 points, the simplest one we can ever get. Okay, let's start from this. On the straight line, we have 2 customers, customer here, customer here. We know the service center bed to be built in the middle. This is our goal. Assume at the beginning we didn't see through this. We don't have the right insight what are we going to do? Yeah, we get start somewhere. Let's pick a random location and build our service center. And in this case, the total distance will be here and here. All right, that's our starting point. It's not perfect, but better than nothing. Let's see if we can improve. There's two directions we can go. We move our service center left or move to the right. See the trending. If we move it here, the total distance will be this one plus this one. We can see total distance is smaller. So this is an improvement. This one is we get a total distance larger. So it's the wrong direction. We are not going through this direction. We go here. So each time we move one step away from where we were. So we get here. Next iteration, we will move left one step away. And we move right one step away. We know this location is no better than this location. But this location decreases our total distance. So we move here. This is logical choice. We either stay or we move left, move right. Which one? Obviously, we move to a better position. And we keep doing that. Each step, we are closer to our goal until we are very close. And this time, let's pause and think. Should we do something different? Should we be more careful? This is our goal. We are so close. Let's zoom in. Here, I move from the right. This is my previous position. This is here, my current position. So if I need to check the next left position will be here. And if I see, compare with this position is worse because it's move away from the goal. This one I already know better than this one. So among left to right, the best choice is stay where I am current is. So no improvement. What do we do? Probably we should take a smaller step and try again. So here, this time, if I decrease the step, I need to check here and here. This one didn't bring me closer to the goal, but this one do. So I take this one, move here. The next, I will try this point and this point. Neither is better than the current location. So what I'm going to do, I will take an even smaller step. So that brings me to this point and somewhere this point, right? This point move me away from the goal. This point bring me closer to the goal. So I take this one. As you can see, I can keep doing that. Next point, I will try this and this. If one of them is better, I move there. If they're not better, I shrink my step. So eventually, my step will be so small. It is even smaller than some threshold. I know the calculated total distance and the real total distance is close enough, so I can use the calculated total distance as my answer and return. Okay, this is one-dimensional problem. The same intuition can be applied to our problem, which is two-dimensional. As we can see, this is our coordinate, x and y. This is our customer. Service center problem here. Assume we make a bad initial guess. We are here. It doesn't matter. We calculate all the total distance and we get a number. Then we try to see if we move away from our initial guess. Do we improve? We move step away, up, down, left, right. For each dot, we calculate total distance. This one seems to give us a better total distance, so we move there. And we do the same, up, down, left, right. This one seems better. And we keep doing that. This one seems better. Up, down, left, right. So we keep see which one give us a better position, and we move there. Okay, again, we are so close to our final goal. This time we pause and see if we need to change our approaching strategy. This is a goal right there. We are here. The next left is somewhere here. This is where we came from. Up, down, up, down, up, down, left, right. None of them help. So what do? We change the step. Take a smaller step. Up, down, left, right. Since this one brings me closer to the goal, so I take this one. Then I do the same. Up, down, left, right. Which one bring me closer? Looks like this one, so great. Then I try again. Up, down, left, right. None of them help. Then what I do? I take an even smaller step. So I check up, down, left, right. Okay, this one brings me closer, so I move there. And you can see I keep doing this up, down, left, right, and get even closer. So each step, if I get an improvement, I keep doing that. If there's no improvement for all those 4 neighbors, I decrease my step size until the step size is so small that the calculated total distance and the real total distance has no difference, and I return the answer. We can expand this intuition to higher dimension, like if we have this 3 dimension and our service center is in the space. So in the space H, our service center is somewhere in the space. Then we get an initial guess. This time we have more direction to explore, left, right, up, down, and front and rear. So all those directions, anyone give us improvement, we move there. Say this time, go to the Z direction, give me a better total distance, I move there. And again, I try up, down, left, right, front, back. This one say give me a better solution, and I keep move zigzag like that until I move very, very, very close to the goal. Then I shrink my step. Right? This is a general problem, linear for global optimum point under linear constraint. Instead of like 2 dimension, we can have 4 dimension, 5 dimension until n dimension. We have a function with many variables. This function, we want to achieve the global minimum or maximum. How we are going to approach? We get an initial guess, doesn't matter. Then we fix all the other value, just to move one variable to different direction, increase and decrease 1 unit, increase and decrease 1 unit, and see if any of those change help. If this doesn't help, doesn't matter. We fix this variable and the other variable, and we just change x2, increase, decrease, see which one give me a better maximum or minimum value. If increase, for example, increase x2 do help, Then what I'm going to do next I will move to x2. Multiply the x2. This is my next position. The other stay the same. And I move there. And then I do the same thing again, fix the other, increase, decrease x, see if I get any improvement. If do, I move there. Otherwise, I fix those, increase this, and so on and so forth until I approach. I'm close enough to my goal. I need to shrink my steps. And if my step is shrink to a very small number, then I know this is time to return the answer. Okay, with this intuition, we are just one step away from the final solution. Where step is big enough, we are keep iterating. So this is a problem. Problem description requires us to get the arrow below this threshold. So our step could be very generous. We have a much smaller threshold for the step. Okay. If in each iteration, what we are going to do is we are going to explore all the directions up, down, left, right. And for those directions, we calculate the next move we will going to be. Okay, once we have the next move, we see if this is an improvement or not. If this is an improvement, we get a smaller total distance. What we are going to do, we will replace our answer with this solution, and we move there. And once we explore all the four directions, we can conditionally decrease our step, cut them half. But as I said, it's conditionally decreased. What condition we need to decrease? Let's take a look how we approach. At the beginning, we aggressively approach our goal. We didn't increase because each iteration we find a better position. So we don't decrease our step. We aggressively approach our goal until we are very close to our goal. This time we consider take a cautious step. For example, here, all those four directions didn't give me a better solution, then I decrease my step and try again. So if I find any solution in the next iteration, a better solution in the next iteration, I keep the step. Otherwise, I shrink the step. This is the logic behind the condition. So I need to have a flag has improved. Initially, we say has improved force. But here we find improve, so we need to update. We only update step when there's no improve. So at the end, the step is so small, we can return our answer. Okay, we didn't give the initial location, which is not that important. You can give it anywhere in this grid. As you can see, this is give us the right answer. We can submit. Okay, this is the answer. One of the follow-up question could be what will be the time complexity. We don't need to mention space complexity, which is a one. Time complexity, we need to analyze. Take a look at this picture. Say in the worst scenario, our goal is on the top left, but we start at the bottom right, the worst possible location. But doesn't matter. Each iteration we get one step closer, so we need to go through the whole map until we reach here. Then we go up until we reach here. Once we get 1 unit away from this goal, we need to shrink the step. So each time we shrink half. After 4 shrink, our size is less than 0.1 of the original size. So roughly like 4 shrink give us 0.1. We want to achieve this goal that roughly equal to 4 multiplied 10. So after 40 shrink, we will reach this goal. So the total step will be the moving step, which is the map size plus 40 shrink steps. For each step, we need to calculate the total distance. We need to calculate total distance. We need to iterate through all the customers. So this is the total time complexity. And if we look at further, do this travel really necessary? The answer is no, it's not necessary. Our step is too small. How about we take like 100 at a time? Our first guess will bring us all the way down here in just one step, right? We don't have to travel many steps. The first guess will bring us here. The second guess will bring us almost to the goal. Then we can start to shrink. So instead of R plus C steps, we just need a few steps, 1 or 2. Within 10 steps, we should get to our goal. Then we shrink. So this is totally a constant. Finally, our time complexity will be OM. And this is a good observation if we use this knowledge to improve our final solution. We increase the step size and we run it and submit. As we can see, it is a faster algorithm. So this is a good example. We use the coding knowledge plus mathematical intuition to reach the goal. So this, we don't need to be very strict on the mathematical approve. You see, this estimation is quite generous. Here we see this is a threshold. We give a much larger threshold so that we know we are precise enough. And why this approach could give us the result? Actually, what we did is when we explore all those 4 directions, we actually take the partial derivative and go down the gradient of this function. So once we go down the gradient of this function, eventually we will get to the value, if there is any in this function. Anyway, prove this, we will need a mathematical paper, but just a little bit of intuition should bring us to the final solution. And if we want to have some takeaway, the takeaway is have an initial guess, no matter how worse it is. Then we observe what will be the formula. Then we try arrow or the possible directions, find one of the move can improve our final goal. We move there and try again until we reach the get close to the goal. Then we do some reflection, try to take a careful move, and until we reach our goal. Okay, this is a very good example.